amine benzyne amine cross linking. Now, these products, as you can see, this is a cross link product and infusible product. So, they will be having good resistance to impact, solvents, moisture, and they also have high strength and dimensional properties. As a result, they are used in several applications like electrical switches, combs, handle of various utensils, and so on. There are many applications you can imagine for this application, this compound. So, these are phenolics, as I said, is a reaction between. Now, quickly move to the next one. In this case, we have formaldehyde with either urea in this melamine utensils. So, you get again cross link product, and reaction is controlled by reaction controlled by pH and temperature of the medium. And the reaction is stopped when by bringing the reaction to the pH, cooling down the temperature and bringing the pH to near to the neutral pH. Now, the reaction, say I will show you this reaction, formaldehyde with melanin, which is very commonly used in making the utensils, as I said. First step, it will be like pre-polymer or intermediate pre-polymer or intermediate product, just like the phenol formaldehyde case, product, intermediate product, and then we will cross link by heating in presence of added acid catalyst, which basically cross link these polymers, and you get like this, just the structure. So, that is a repeating unit. So, this is a melamine formaldehyde polymer, or in short melamine polymer, which basically are used in preparation of that coating the utensils, which we commonly use. And in terms of application, this melanin also I do what to write. So, basically okay, we do not need to write too many applications. Basically, you know this is very common, the melanin utensils you use. Okay, so we basically has given 7 type of example and the synthesis process and some applications of them. So, next we will move. Before I move, I just wanted to show the there are other examples in your book. This is a copied from your NCERT book. So, there are other example given in the book. So, you please go through the polymers, the monomers, their structures and their uses. This is just you have the information. So, you have to remember the structure, the name of the polymer, monomer and their uses. So, please read this from book and remember, try to remember some of the structure and names of the polymer and their use. Ethylene. So, next what we will do, we will discuss the next topic, which is about rubber. Now, obviously, rubber, when you talk about it must be elastomer, where basically most common is the rubber band, where you basically stretch a rubber band, you can stretch it easily, and then when you stretch a rubber band, you can easily stretch, and then when you leave this, it will come back to the original dimension because of its elasticity. So, that is what we mostly associated about rubber. So, they are basically elastomer. And the use of rubber is from a long time ago, about 16th century people were using rubbers for making playing balls or waterproof clothings and erasers and all these things. And about 19th century where the technology of rubber started. And the technology was started because initially rubber had lot of problems. Rubber would get basically it will soften and get sticky at warm temperature, at higher temperature, and when you bring the temperature, the rubber would become hard and brittle. So, these are the, and it will soluble in nonpolar solvent. So, these are the some of the reason why the rubber has a did not have applications or in many ways it could not basically expand its applications. So, in 19th century with the discovery of vulcanization is what when the rubber gets actually the application of rubber expanded in many areas. So, it was discovery of vulcanization of rubber. It was discovered by the vulcanization of rubber by using sulfur. And it was discovered by Charles Goodyear. You have probably heard Goodyear tire, and it was done on long back 1839 in USA, and he filed patent, and which was granted. The patent was granted in 1844. So, by doing the vulcanization, what happened? The elastic properties was improved. Elastic properties were improved, and tackiness was eliminated. Now, at the same time, there is another scientist, Thomas Hancock in London, who also discovered similar vulcanization method, and he also filed patent at 1843. This is the filing year, and it was issued, the patent was granted, which was granted, the patent was granted after the Goodyear's patent at 1844. The first patent, Charles Goodyear's, he basically improved the vulcanization process by using a large amount of sulfur, and which basically makes a hard polymer, hard rubber material, which were more useful and probably used for tire material. The first rubber which was obviously useful and utilized was natural rubber. We can write just NR for natural rubber, and natural rubbers is obtained, it is milky white. You probably have seen, if you have seen a rubber tree, it is a milky white latex which contained colloidal dispersion of rubber hydrocarbons, or you can call whatever particles. So, this is obtained from the bark of rubber tree. You know, if you probably visited Kerala, or sometimes you probably have seen the rubber trees, then from the bark you can get this milky white coming out, and you can get natural rubber from bark of the rubber trees are basically abundance in the South Africa. It basically useful, and the structure, if you look at the structure of the natural rubber, its chemical structure is like this. This is a natural polymer. Obviously, we got the polymer. It is not that we had synthesized the polymer in the lab or plant. So, the polymer was obtained, and then structure was analyzed, and it was found like this. So, you can consider this is the repeating unit of the polymer. So, if you look at this polymer, you can see that this is a polymer you obtained. So, it is not that we have you are basically synthesizing a polymer from monomer, but if you think that this is, if you have to name that, generally how polymers are named, the polymers are named just adding poly and the monomer from which the polymers are formed. So, if you talk about ethylene is the monomer, we write polyethylene. Vinyl chloride is the polymer, so we write polyvinyl chloride. Polystyrene is the monomer, so we write polystyrene. If you ethylene glycol and terephthalic acid is your polymer, and you obtain ester from that, we write polyethylene terephthalate. So, how do you name polymers? Is basically add the term poly and then the monomer or the repeat unit from which you got the polymer. So, basically we have this polymer now. So, if you want to name this, we have to imagine from which monomer we can synthesize, or theoretically which form monomer it was synthesized, and what is the structure here. Now, you can see there is a double bond here. So, as you have seen, you know that if there is a double bond, there could be two possibilities, there is a cis configuration or a trans configuration, and in this case you can see this is a cis configuration. So, we can think that this is a cis configuration, and what is the monomer, probably it is obtained we can think that this is obtained from this monomer. So, this is a single bond, not double bond. So, if we think about this is the monomer, then we can think about a initiator which can react, and you get the double bond here and you get the active center here. So, you get from here you get ICH2 . So, this is the active center, it can react with further this monomer and you can get this polymer. So, we can imagine that this is the monomer for this polymer, and what is the name of this? This is a 1,3,2-methyl 1,3-butadiene. Okay. So, basically we can think this is a monomer which is a 2-methyl 1,3-butadiene. Now, the attack in this case this polymer is through first carbon and fourth carbon. So, we are writing cis 1,4 poly 2-methyl 1,3-butadiene. So, this is the name of this polymer, natural polymer, and this 2-methyl 1,3-butadiene is also commonly written as isoprene. You can, I hope you understood why it is 1,4, because sometimes you can just add here, the active center will be here and you can make a polymer with this. So, that will be a 1,2 addition. You can have the polymer made through this only using this double bond. So, that will be a 3,4 addition, and in this case it is a 1,4 addition. So, that is why you are writing, because the cis configuration we are writing cis 1,4 poly 2-methyl 1,3-butadiene, and 2-methyl 1,3-butadiene is also written as sometimes poly isoprene. So, the polymer natural rubber is also sometimes written as cis 1,4 poly isoprene. Now, these have very weak interactions between the molecules, and because of the cis configuration you can imagine that the polymer chain when it grows it coils up, and when it is coils up, what happens, you can stretch, while you stretch you basically you gives the retractive force and you get the elasticity because of the coil configuration. And these double bonds also help us further doing chemical reactions on the double bonds, which is what the vulcanization step is used to do. So, we will now learn what is vulcanization. Z or S, whatever you can write. Now, why do we require vulcanization of rubber? This natural rubber becomes soft, as I mentioned, soft and sticky at greater than 335 K. It becomes hard and brittle less than 283 K, and this limits their application, and it at low temperature is also a high water absorption capacity, and this is soluble in nonpolar solvents, and it is not resistant. So, non-resistance resistant to attack to oxidizing, because of the double bond it can easily oxidize. So, basically it is not resistant to the oxidizing agents, which makes their use limited. The natural rubber is applications got limited, and that is the reason we require to cross link this rubber, and that is done using sulfur as a cross linker, and that is what called vulcanization step. So, you take the raw rubber, maybe I can do it in the next page. So, vulcanization is you take the raw rubber plus sulfur plus an appropriate additive, which basically accelerate this cross linking process. I am not going in the details of what these additives are, but an appropriate additive which basically helps in accelerating this this cross linking reaction. You heat it up, generally temperature is 273 to 415 K, and you have to keep it for, it is done for long hours. So, it takes time, and the amount of sulfur is small, probably between 1 to 5% in general case, but it could be in even smaller or even higher if required, and you get this cross linking different cross linking products, and we are just writing few structures. Remember, the base structure was polyisoprene, 2-methyl 1,3-butadiene. This is one possibility. The other possibility could be so, these are basically cross linking happens between two natural rubber chains, which are basically nothing but polyisoprene, cis-1,4 polyisoprene, what we talked about earlier. And in case of if you add 5% rubber sulfur, sulfur in it basically cross link heavily, and it can be used for tire application. So, basically tire rubber, it becomes a tire rubber, and it becomes resistant to a lot of chemicals, solvent and all these things. So, this is what natural rubber is, and how it is the property of natural rubber is improved by cross linking with sulfur, with the process is called vulcanization. Now, this is the story with natural rubbers post vulcanization went till 1939-40, during which the World War II was happening, and during World War II what happened, there was a shortage of these natural rubbers from the countries which I mentioned earlier. So, there was a huge requirement to make synthetic rubbers, so that we do not have to rely on the natural resources like rubber trees. So, at this time around 1939-40, where the first synthetic rubbers came in. So, synthetic rubbers are basically any vulcanizable rubber like polymer which is capable of getting stretched at least 2 times than the original length, and this stretching is reversible. Okay, so it should come back when you release the stretching. And these are mainly the synthetic rubbers are mainly of homopolymers of homo or copolymers of 1,3-butadiene and their derivatives and butadiene and its derivatives. Example as is first is SBr, which are styrene butadiene rubber. The example we gave in earlier Buna S, which is a 1,3-butadiene rubber with styrene, and Na was used for sodium, which is used for making the polymer. Seconds would be this polychloroprene rubber, where it is synthesized from the monomer chloropene. So, this is chloroprene, and you can get and this polymer is called neoprene. So, neoprene is basically polychloropene. So, neoprene is nothing but polymer of chloroprene, and this is neoprene is very resistant to vegetable oil and mineral oil. So, that is why they are used for in conveyor belt, gloves, gaskets and horses. So, these are some of the example of neoprene would be gloves, gaskets, horses and so on. So, you can read books or get this information from any other. These are just for remembering. The third category of synthetic rubbers is nitrile rubber. These are we are talking about synthetic rubbers or NBR, where we get a copolymer of 1,3-butadiene plus acrylonitrile. This is 1,3-butadiene plus we have know the structure of polymer of this, and this copolymer I am not writing, I can write the structure. This is called Buna N. So, 1,3-butadiene, N for nitrile and Na for sodium, where used for doing this reaction, and this is resistant to petrol, lubricating oil, organic solvents, and this is it's used for making oil seal, tank lining and so on. So, we talked about now natural rubbers and synthetic rubber, and the last I quickly go through in next 5 minutes is one important topic called biodegradable polymers. When we talked about polymers, different stages of polymers preparation and uses, we talked about that in the last step, which is very critical because nowadays wasting the polymer waste is becoming a problem. So, basically managing the polymer waste which is not degradable by environmental conditions becoming problem. So, it is basically if we can develop new biodegradable polymers, it will be easy for us to handle this polymer waste. And by definition, what is biodegradable polymer? Is a polymer capable of undergoing decomposition into carbon dioxide, methane, water, inorganic compounds and biomass, predominantly done by enzymatic action of microorganisms like bacteria. So, basically it is these ingredients and which is mainly done primarily by enzymatic action of microorganism like bacteria, and carbon dioxide and water is produced when you do this decomposition in presence of air, and methane is produced in terms of when you do it in an anaerobic condition or in absence of air. And most of the natural polymers like cellulose, chitin, starch, proteins or polypeptides, they are all biodegradable enzymatically. So, it is not a problem if you can make polymers from these natural polymers, they will be biodegradable by their own. The problem comes when we have we do synthesis from deals with synthetic polymers, and the synthetic polymers the aliphatic polyesters are generally biodegradables, degradable polymers. Example would be polyhydroxyalkanoates or PHA in short, and example is poly beta hydroxy butyrate, co beta hydroxy valerate. In short, it is called PHBV. The structure is formed from 3-hydroxy butanoic acid plus 3-hydroxyvaleric acid. I am not writing the structure because I have to finish in a minute. Valeric acid, and this gives you a copolyester, which we in short we write PHBV. The structure is you can write the structure yourself. The other polyesters like polylactides, which are formed from polylactic acids, or polylactides co-glycolides, which are formed from copolymer of lactic acid and glycolic acids. and polycaprolactones. These are the example of biodegradable polymers. So, with there are one example where you have the copolymer of nylon 2 and nylon 6, you can read from book. This is also a biodegradable polymer. So, what I will do, I will just quickly wrap up and I guess I should have, if I had 5 more minutes, probably I could have wrapped up it more nicely. But anyway, we have studied polymers, and if you recall the first lecture 1, we talked about that and branched. I will wrap up this unit on and branched